All right, so now we're up to the next page is 31 in the workbook, and I'll do a screen share in just a second, but we're talking about momentum. All right, so give me just a sec. All right, and let me get that up on screen for us. Okay, momentum. So for some reason, I didn't put all the good stuff on one page. So the key pages for this chapter with all the definitions and stuff are on pages 31, 32, and 34, but I'm not sure. We'll check it out. So let's start with the basics here. Up until now, I don't know if you've noticed, we've generally been talking about a single object moving around or groups of objects moving around in unison. Well, in the real world, cars crash, balls bounce off spheres, whatever, bombs, separated space, zombies walk in boats. We know these things happen in real life, especially the zombie. But we need to use this new concept, momentum, to address collisions and explosions and rearrangements, and center of mass will also help. So we're finally going to get into some of these big terms. So let's start off here. Momentum, it's a vector. Okay. And it's mv. Don't be jealous. It's not envy. And collision time, delta t. Sometimes I'll just be lazy and call it t. That's the time two objects are in contact. Look carefully at this next one. Force relates to momentum with this result. The average force is given by change in momentum of an object over change in time. Now, sometimes we use the term impulse to describe the term change in momentum. So, and we see that this impulse is like force times delta time. So notice delta P, force times delta time, impulse, they're all the same thing. Now, I think this is a big deal because of the following. You see, this is snuck in here, a footnote, but this is actually a pretty big deal. This is called the Euler, as in the mathematician Euler, Kromer method. And if you want to create a simulation in a computer where you animate motion and have it obey the laws of physics, this is probably the simplest one that does a good job for almost all cases. So not perfect, but yeah, let's just leave it at that. So it turns out this method of coding allows energy to be conserved, which we usually assume is conserved. So that would be a good thing. And what we're going to learn is if you first update a force, then use that to update a momentum using this impulse equation, right? You can get the change in momentum from force and the time. Then we can use that to update the velocity because it's all hidden inside of there. And then we could use that with kinematics. We could use distance equals rate times time if we chop up the time increment small enough. Because if you chop up the time increment small enough, you could argue that, well, I guess let me put it this way. We've accounted for all of the acceleration in this term right here, which gives us the average velocity. And if that average velocity is not a good average, we just chop up the time interval even smaller until it is good average. All right. So that's something that we're going to learn. Let's start by looking at this problem here. Okay, and again, we're using these symbols on page 31 to analyze a simple problem 9.1. I'm going to take a second to draw this up. You can read it and get it on your paper. Nine point one. Notice, just like with energy problems, we have a before and an after picture here. I'm just getting the same picture drawn on line paper. Oh, we're told the collision time. So you could figure that out using video capture, right? You could just literally watch how many frames the ball is actually touching the wall. If you're curious how you could get this information, you could film it and figure out the velocity coming in. You could figure out the velocity going out. You could figure out the time it was touching the ball. This is totally practical stuff. All of you could do with the tracker program already. You could get all that data from any real life collision. All right, let's get this up here. So here it is. All right, there we go. Okay, we're asked to figure out the initial momentum in this case. Oh, and this is before and after. So I want the initial momentum. Somebody tell me what that is or how I would get it. What equation should I use?
Mass times the velocity vector, which is
okay.
So 0.075 times 6.0 meters a second.
You're on the right track, but you forgot something. Okay, you said MV, right? Which is 0.075.
Correct.
That's good. And what was V?
6.0.
Negative.
Right? You got it, Jess?
Yes, I see.
Yep. And so and now we see, oh crap, now the direction matters again. If I could, I'll stick in the I hat this time. All right. And so remember, it's mass times velocity vector. Now, sometimes what we might do is we could say this is P initial in the X. And then I'm just going to punch in these numbers just so I don't have to keep rewriting them. 0.075 times 6. So 0.45. So sometimes what we'll do is we'll include the minus sign, but not the I hat, just like in chapter 2 and chapter 4. So because it's that velocity vector, the minus sign matters. And I'll show you why in just a second. Don't overthink the units. They're just kilogram meters per second. We don't have a special unit for this. Okay. All right.
Momentum is a lowercase p, right?
That's right. This is a lowercase p. Yep. Sorry if that looks a little bit capital there. I try to distinguish it. Like if I drew that would mean a capital P to me. That's how I tell the difference. But lowercase p. And remember, rho is this kind of curly. So this is a P, this is a capital P, and this is a rho. Okay. Those details end up adding up after a while, for sure. Okay. Sorry. I don't know what that is. All right, good enough. Okay. So now, just so I have some room, I'm going to just erase this line. Think to yourself, part B is what's the final momentum? Go ahead and hit it, okay? Let me just rewrite that. That's driving me crazy. So part B, the final momentum is what? I think it's 0.30. It should be 2/3 of that, but positive. Looks like we're doing all 2 sig figs for this problem. Who cares? It gives us an idea. That's pretty plausible if you consider video capture. We'd be lucky to get 2 sig figs. So yeah, okay, this is not bad. All right. So part C asks, let me read part C. What is the change in momentum of the ball?
0.75.
Exactly. It's not 15. It's going to be final minus initial. So we actually get the 7.5. And that's what we were looking for, just to try and make sure we don't screw up these little details. All right. And this is why the minus signs have to be in there. Because if we talk about an object changing from moving left to moving right, it matters. Think about this. Let's say it came in at 6 and left at 6. The change in momentum would be 0.9, not 0. That's a huge difference, right? So the sign matters. Enough said. What's another name for this change in momentum? Do you remember?
Impulse.
Impulse. Good. Oh, and I missed some questions in the chat. Sorry about that. Oh, thanks. Oh, Gonzalo, you probably realized I'm better at responding to voice than chat. Sorry about that. All right. So thanks for unmuting. I appreciate it. Okay. And I do get to the chat, but sometimes I just don't see it out of the corner of my eye when I'm up here. That's all. Okay. So part D, that's impulse. Okay. And then just to be clear, let's put some vectors on here because we're learning. I'm just going to do this and call this in the I hat. And this here, just we're learning. We might as well have all the notation up there. So if you're curious, this is part D as well. Part C and part D, impulse. All right. Part E. How do we get the average force?
The impulse divided by the change in time.
Yep. Is it going to be a vector or a scalar?
Scalar. Wait.
Vector. Force is a vector, right?
Yeah, I caught myself.
Yep, you caught it. All right. So that's going to be, I think, let's just punch in the numbers here. I think it's this number divided by this number up here, which I'm just going to punch it in. It's delta P over delta T. Let's write it. So I'm going to punch in those numbers. Whoops, it was 0.75 divided by 0.05. So 15. Now convention is if the first digit's a 1, we oftentimes include an extra sig fig, so I'll do that. And to be clear, it's a vector. In this case, it's a positive number. That means positive I hat. Again, normally we leave off the I hats, but positive would mean positive I hat. Negative would mean negative. All right, so we're good. In this case, does it make sense? The ball was going this way. Now it's going that way. Something must have pushed on it that way. This makes sense. All right, reasonable. Totally reasonable. All right. How would we find the average force on the earth? We just found the force on the ball. How could we find the force on the earth? On the cliff that it hit. Does it help if I ask from over here? It's been a long day. I'm losing my mind.
Negative
of this.
Yeah.
If I push on you, you push back on me the same amount the other way. So by Newton's third law, the force average on the cliff would be negative 15 I hat. All right. Now, if you want the next part, I'm just going to bring up the screen share really quick. It says, figure out the change in the Earth's momentum. So think about this. We know this force. We know this force now. And now we could use this mass and figure out the change in the Earth's velocity. To save you some time, let's open it up. Give me just a sec. Zoom windows. Okay. 10 to the minus 25th meters per second. So this means the Earth would go backwards at such speed that it would pass a nucleus in approximately 320 years. Okay. The Earth is, for all intents and purposes, unchanged by this. So it's not that the Earth doesn't move backwards. It's that the amount it moves backwards is so small, it's negligible. There's a subtle difference there, but that's the thing. Okay. So there's that. That does kind of crack me up, though. All right. So now we understand this problem right here. All right. I don't know what that was. Okay. Sorry, I got distracted there. So let's go into here. Here's a variation on this problem just to kind of force you to deal with this. And if you're curious about the like how this might look with a tracker, I think it's 9.48. I love how I call my own questions awesome. Maybe I should let you guys review these questions and give me the names. Terrible, brutal, made me want to quit physics. You decide your own adjectives. I'll call them all awesome or excellent. But yeah, okay. I'm losing it. Let's get to this. All right. So you could do that problem later. Okay. Do 9.2 later to get a variation on what we just did. Okay. Let me pause before we go on. Any questions? All right. Now we're going to do a new topic called conservation of momentum, just like we had conservation of energy. Again, conservation just means initial equals final. Let me walk you through this. Let's say we have two objects. By Newton's third law, we know they exert equal but opposite forces. So 2 on 1 is equal but opposite 1 on 2. We have defined this as change in momentum over change in time. If it helps you see this, let's think about something here. Watch this. I think you agree that force equals ma, right? I think you're pretty good with that. But wait, isn't ma m times dv dt? Yeah, it is, right? But wait, I'm going to cheat and pretend mass is constant all the time and pop it in here. Well, that's just ddt of mv. Well, that's just force equals the time derivative of momentum vector. That's the same thing that I'm writing right here. All I did was I replaced force with dp dt, and then I used deltas to get an average or an approximate result. Here's a crazy thing, people. It turns out defining force this way works when we go to speeds near the speed of light. This other one will not work. Also, this equation is valid even when the mass is changing or not. And so it turns out it's a stronger way of writing Newton's second law to use this. Now, again, from a practical standpoint, many times it's easiest to use F equals ma, and that's why we started with that. However, this is a more fundamental result. This is valid both at low speeds and at speeds close to the speed of light. That said, let's get through this damn derivation. They have the same delta t's. That means I get equal but opposite changes of momentum. Okay. That means if I put the two momentums on the same side, the total momentum doesn't change. So we say it this way: the initial and final system momentum, system final, and system initial are conserved. Okay, momentum is conserved. The momentum of single objects will change. The momentum of the entire system will not change. Now, if we want to use this result, How do we use that? Whoa, this is a lot of words. First, we're going to look at a problem. Is it okay to use conservation momentum? What do I mean by that? Are the external forces negligible? If you have external forces, they are going to do work, and that's going to be complicated, and that will change the momentum. So we don't want to have external forces. Now, it turns out in most collisions, the collision time is usually very small. And if it's very small, sometimes even large external forces like gravity are negligible. Or you could do this thing on a table, and the table can provide an upwards normal force, so there's no net external force. So there's all kinds of ways we could do this, but even for a ball, like the problem we just did, when this ball hits the wall, gravity is acting on it. Technically, we know it should hit the wall and kind of bounce downwards a little bit. But look at this collision time. That is very small. And so during that collision time, the amount of up and down velocity introduced is negligible, and we could ignore this crap. So we'll just assume that these two velocities are so much bigger than the one that's caused by the gravitational force. We could ignore gravity, the external force, during this collision. And we did. Okay. All right. So basically, is the collision time short or not? Or is it, are there negligible external forces for some other reason? Next, draw before and after picture. I don't know if you've noticed, we already had one of those. It's just like the energy chapter. One picture is not enough. Okay. If you're not sure which directions the objects goes, you're just going to pick one and go with it. I'll give you an example in a minute. Well, like this, suppose you weren't sure which direction it should be moving in the final picture. Okay. Yeah, if the final answer is negative, it moves opposite the direction you drew. More on that in a bit. Here's the conservation momentum equations. Here's some blah, blah, blah. Okay, so there's a bunch of stuff. Plug it in and do something. So just remember that this page is here. Page 32 gives you some ideas of how to do conservation momentum problems. Great. All right, here's one. We have already alluded to this a little bit. There's a classic question everyone asks. What if everybody went to the North Pole and jumped at the same time? How fast would the Earth move the other way? Well, we kind of did the problem already, so I'm going to let you kind of think this through, but let me just give you a clue here. Let's first estimate the number of people on Earth. How about 10 billion, right? So that's about 10 to the 10th people, right? What's the mass? What's the average mass of a human being? Give me an easy number.
200 pounds.
200 pounds. Okay, how about we say 100 kilograms? So all the people on the Earth are going to weigh about 1 trillion kilograms. Notice the mass of the Earth is 1 trillion times larger than that. So we expect no matter how fast the people jump. Now, I did a quick calculation earlier today, and I think for about a meter jump, this would be 5 meters per second. So imagine if everybody on Earth was as big as me and could jump like some of the best athletes that have ever lived. And we all jumped at the same time. The Earth would be moving downwards at 5 divided by 1 trillion meters per second. So yes, the Earth would move the other way, but it would be negligible. Okay. All right. That's enough said on that one. All right. Any questions on that?
Is that the same as the recoil speed, like part E says?
Yeah, the recoil. Exactly. So the recoil speed. So recoil speed is the recoil of this object. And that actually motivates me to show a video here. Let me give you an example of what I mean by recoil speed. Thank you for asking that. Hold on. Let me go to this one here. Okay, so this is Angus. He's the guy that does all the work behind the camera, and I needed him to do this. So Angus is about 145 pounds, and that ball is about 6 or 7 pounds. Okay, so Angus is what, 20 times bigger than that ball. He's going to sit on this hovercraft, and he's going to throw that hovercraft, or sorry, not throw the hovercraft. He's going to throw the ball to the, I don't know which way we would call it. He's going to throw the ball this way. Now, for reference, you can see there's different meter sticks in here. This blue line in here is about 2 meters. So he's going to throw that ball to me in just a second. And then the idea here is he turns on the hovercraft. The hovercraft reduces friction between himself and the ground. That's just a little leaf blower there. So when he turns on the hovercraft, the friction is reduced to near zero. When he throws the ball to the right, you should see his 20 times smaller recoil velocity to the left. See it, Bowie, up there? Notice how fast the ball moved relative to Angus, right? All right, so there's that one. Now let's go to this one. So in this one, I weigh 240 pounds versus Angus, who's 145. So in the last one, Angus was the big mass. He threw the small mass, and he had a small recoil. Now, Angus is the small mass, right? So different objects, their mass could be big or small depending on what the other mass is. So in this scenario, Angus is going to get on there. Let's get full screen for all this horrible glory. What we're going to do is we're going to push as hard as we can on this cardboard tube. And so we should see the recoil. Whoops. Hold on. Shoot. Okay, let me get my annotations off here. It's driving me crazy. Sorry about that. So we're going to turn on the leaf blowers, push as hard as we can, and let's see what happens. There we go. Hard as we can. And I just fall over. So notice I'm just too big for these damn hovercraft. And then I started laughing so hard and I got ab cramps and I was having trouble standing up. It cracked me up. So you can watch me as I flail about here and I'm just like, oh my God. All right. So that was, you can see Angus is laughing too. So let's see if we can get a better version of that one. Here's me versus a chemistry professor. All right. And that's very important. We've got to somehow try to shame anyone in chemistry just because that's what physicists love to do. It's because we're jealous that they have a better lifestyle than we do. But that doesn't mean we won't make fun of them. Oh, go ahead.
Is that the same video? I thought. I don't think it switched.
Oh, whoops. Did I not switch? Thank you. Oh, there. Sorry about that. There we go. So Gottlieb is he's another 145 pounder. So yeah, and so when we do this one, I think you could actually see the recoil. Now keep in mind here, let's do the masses. Let's round. Let's say I'm 250 and Gottlieb is 150. Right? So 250 out of the total mass of 400 is 5/8. So I should be going backwards at 5/8 in units of some velocity, whereas he'll be going, wait, no, I'm 5/8 of the mass, so I'll be going backwards with 3/8 of the speed. And he's 3/8 of the mass, so he'll be going backwards with 5/8. So we should see him going slightly faster than me. And I think you agree that's slightly true there. All right. So that's good enough on that one. Sorry it took me so long to babble that out. Questions about that junk? Okay. I'll say that's a no.
Even though there's no friction, the mass still takes into account.
Yeah, exactly. Yeah, let me give you another example here. The mass, so the mass is what matters, right? So my normal force and mg are canceled by the hovercraft. Friction is eliminated by the hovercraft. So this is a pretty good pure momentum, right? So we've eliminated the external forces in this way. Is that what you were asking, Alonso?
Yeah.
All right. So then let me see. I have, let me see. Where is that one? Let me give you an example of an inelastic collision. an inelastic collision here. So in this case, notice those objects hit and stick together. This is actually a special kind of inelastic collision called perfectly inelastic. You don't need to write any of this down. I'm going to go through a summary sheet in a minute. So just listen and kind of learn some terms, and I'll summarize in a minute, okay? Here's what an elastic explosion might look like. So in this case, I've got two objects. This is actually very similar to what we just did. One of the masses is 420, the other is 210. And so when we launch this thing somewhere, the idea is, maybe eventually, at some point I'm going to launch this thing. Okay, so now you can't see this right now, but in a second my arm gets out of the way. There's a rubber band. I hit pause. There's a rubber band right there. And so the idea is that rubber band is acting like a spring. So here's a case where momentum is going to be conserved. The initial momentum is 0. That means the final momentum has to be 0, right? But the final momentum will be P2 initial plus P1 initial, the two carts. And so one of them is going to have to be positive and one of them is going to have to be negative. This one will have a negative velocity. This only records speed. This one will have a positive velocity, and that screen is going to record the speed. We expect if the masses come in a ratio of 2 to 1, the speeds should come in the ratio of 1 to 2. Now let's run it and see. Not perfect. Let me get a running start at that one just in case. Just so you see that I'm not making this up. There we go. It's not perfect, but it's approximately right. Okay, let's do another variation. Again, I'm going to explain what all these terms mean. Here is a, actually that's, let's show, here's an elastic collision. So this one's a little bit different. In this case, whoops, let's run that again. So this is quite mesmerizing when you see it. Give me just a sec. The idea here is I have two 300-gram carts. These are each 300 grams over here. And this is a 410, and this is a 210. And the idea is we're going to hit them. And this time, there's a clock recording the initial speeds of these. I did that just so I could make sure I got a video where the two were actually going about the same speed. So you're going to see these two carts slam into them, and watch what happens in this case. Here we go. Ooh, and let's slow it down just slightly. Let's do half speed. Here we go. They hit at about, whoa, look at that. Do you see a big difference? This one bounced backwards. Did you see that? That one right there bounced backwards. Let's try this again. I don't know if I'm boring you or not, but here we go. See that? And let's just watch this for a minute. So notice when a heavy object hits a light one, the light one goes flying off the other way. But when a light one hits a heavier one, it gets bounced backwards. That's the pattern here. This is complicated. There's a lot of different scenarios. I just wish there was a way we could summarize all this in one shot, and we can. There's a better way. Let's take a look. All right. So we've been looking at all these collisions and all this stuff. If we want to understand this stuff, let me just go to this page really quick. Okay, so this is page 34. Sorry about that. 34. This is just some different words we kind of have to use. So if you're reading a textbook, you can understand it. Okay, perfectly inelastic is a type of collision where the objects form a single mass moving together in unison. Okay, instead of having separate final speeds, they have one common final speed. Energy is lost. An example would be two cars collide and get stuck together, or a lump of clay hits and sticks to a block, or problem 9.6. What if they completely bounce off? That term is called elastic. I like to think of rubber bands are like elastic bands. So rubber bands cause bouncy collisions, perfectly bouncy. Look at the subtle difference between a perfectly inelastic and an elastic. In an elastic, energy is conserved. In an inelastic, energy is not conserved. And that's actually true whether it's perfectly inelastic or just regularly inelastic. So, okay. Believe it or not, two pool balls smacking into each other, you actually have negligible loss of energy, or two marbles. A steel ball bouncing off a steel plate loses very little energy. It's not perfectly elastic, but it's pretty damn close. It's a lot closer to elastic than say, perfectly inelastic. The objects do not, in general, form a single mass. Here's a weird one. Let's say you have a planet. Let's say this planet is Venus. And let's say you're sitting on Earth. And let's say you want your satellite to launch from Earth and get out to Jupiter. You can have your satellite whip around Venus. That is an elastic collision with Venus because it never actually interacts with the atmosphere and it experiences drag. It just whips around the planet and you could actually double the speed. So if you remember Vija, they did this thing called Venus, Earth, gravity assist. Whatever. So this was a big thing. If you want to look up Vija, that's basically 3 elastic collisions. They had the satellite, they launched it from Earth, had it elastically collide with Venus, then Earth again, and it made it faster to get out to the outer planets by colliding with Earth twice extra. All right, so whatever. You read about that on your own. It's kind of cool though. All right, whatever. So let's do this. Inelastic, I call that imperfectly bouncy. Most real life collisions are this type. Okay. However, many real life collisions can be approximated by the others. That said, you lose some energy. However, the blocks do not form a single mass. Let me get to the chat. Gravitational fields like a slingshot. Yes, Gonzalo, absolutely. Gravitational. All right. Yeah, the slingshot effect. If you've ever heard the slingshot effect, same thing. Right? It's basically elastic collision effect. All right. Now here's the deal. Let's get down to explosions. That's where things separate. Okay. Think of them as a perfectly inelastic collision played in reversed. You start with one object and end up with fragments. Okay. So typically you gain kinetic energy. Imagine a bomb sitting on the ground. If a bomb was just sitting there, it would have no kinetic energy. When it explodes, the fragments have tons of kinetic energy, and that's from converting the chemical energy in the bomb materials. So you could even do this if you throw a bomb. If you throw a bomb with some speed, then the fragments are going to have different final speeds, et cetera, et cetera. So here's some different examples. Great. This is like Angus and I sitting on the hovercraft and we push on each other and we explode outwards, or the 2 carts that were pushed apart by the rubber band. All right. Oh, wait a minute. The 2 carts that were pushed apart by the rubber band actually obey this one, the elastic explosion. So in this case, notice again the difference. In this one, we don't use conservation of energy. In this one, like, let's say we're talking about the spring one where there was a rubber band or a spring pushing apart 2 blocks. The initial energy is stored in the spring. The final energy is stored in the kinetic energy of blocks 1 and 2. So that's a conservation of energy equation you could write. In addition, you could use this conservation of momentum equation. But notice all of these had conservation momentum. That is the thing that is common to all of the different pictures and videos I've been showing you all for the last hour. Momentum is conserved. If you want to know how to handle these problems, That is what I was saying right here. This is a practical guide on how to solve problems, what you need to do when you're doing a problem. You draw a before and after picture, you prick something, you write down this equation. If it says elastic somewhere in it, or if it implies energy is concerned, then you could do energy equations. Okay, plug in some stuff, do some work. All right. Whew. Pretty intense, right? Let's try a quick concept question, then do a video question and call it a day. So let's do 2 more things and then we'll call it a day here. So let me get back in there and do a concept question. How about 9.5 at the bottom of page 33? Take a second to look at it. I'll give you a minute. So at 8:33:33, or 6:33:33, we'll talk about it. All right. During the collision, you've got this bus and an insect. Which one's exerting more force?
Neither. It's the same.
By which, what's the principle that guides your reasoning there? You're right.
Because when it sticks, like that reminds me of the perfect knee inelastic situation we were just reviewing earlier.
That's true. I was looking for a physics principle.
Average.
Newton's third law.
Newton's third law. And so, and you're saying everything you said was also true, Gonzalo. But the principle I was looking for was Newton's third law. Does that make sense why I said that?
Oh, yeah.
Right. Because that's where what you said came from. Basically, we're saying the same thing there. Good. All right. Which one, however, experiences the larger change in momentum?
Momentum is the same as force.
Exactly. So it's also the same. I keep trying to trick you and I can't. I have failed, which is good. So which one has more acceleration?
The bug.
That's right. So let's run this through in pictures. We know that force on one, let me just write on one equals negative force on two during that collision. Well, that says delta P over delta T should be the same. Sorry, it's taking so long. But now we also know if this is the bug has a tiny mass, so it has a huge acceleration, right? Whereas over here, the bus has a huge mass, so it has a tiny acceleration. And so this makes sense. We got to be careful when we're looking at part B. The common thing when we're doing part B, the misconception students sometimes slip into, change in momentum is not quite the same thing as change in velocity. They're obviously related, but the mass matters. So if you could do this same picture this way. Whoops, sorry. M1 times a tiny delta V, right? Should equal M2 with a negative sign times a massive delta V. So changes in velocity and acceleration are linked. forces and changes in momentum are linked. We see that. Any questions on that? That's one thing you're supposed to get out of today. I can't say I've put that on every single final I've ever given, but some variation of this problem usually shows up somewhere. So you better know this frickin' problem, people. All right. All right. Let's keep rolling. Let me give you another video here. Can I get back into here? Let me okay, so here's another little puzzler for you. Hopefully you can still see my screen here. So I'll just hit play on this. Watch the bottom of the screen. Hopefully you can see the mass is right here. I'm just trying to show you that I've got two spheres, 1 and 2, and I want you to see that these two masses are the same. And so I'll explain what's going on in a minute. $36.8. 36 point something, 36.2, basically the same, right? So very close to the same. And now watch this. I'm going to drop this ball. Notice it does not bounce very much. By the way, the other one does bounce a lot. So the other one with the white stripes on it will bounce more. It's more elastic. I want you to tell me which ball is going to exert more force on that piece of wood. Will it be the bouncy ball or the not bouncy ball? What's your gut tell you? They're the same mass. They're going to hit the thing with the same speed. I'm going to put both of them right here at this spot, and I'm going to release them from rest. So we know from conservation of energy, they both fall the same height. They're both going to take the same trajectory. They're both going to hit the board right here with the same speed. Which ball exerts more force? Is it the happy ball that's bouncy, the sad ball, or is it the same? Gonzalo says bouncy. What do you guys all think?
The hard one, it doesn't absorb the impact.
Okay, and so why do you say that? What's kind of the thought process?
It doesn't bounce.
Okay, so if it doesn't bounce, how much does its momentum change? A lot or a little? It's going this way, right? So let's do the sad ball. Okay, or the not bouncy. The not bouncy ball, we know it's going to come off of here. Let's just make up a funny number. Let's just say it's moving this way at 2 meters per second. I have no idea. Okay, just pretend it's moving at 2. At the end, it's going to hit this thing, and then how fast is it going to move after it makes impact? If it doesn't bounce, what's the final speed?
0.
0. Now compare and contrast that to another scenario wherein we've got this other ball. It's going to move again at the same speed, 2 meters per second, but it's bouncy. It's going to hit the board right here, and it's going to bounce backwards. Assuming it's perfectly bouncy, how fast would it be moving after the bounce?
2 in the other direction.
2. Which one exerts more force? Which one has the larger change in momentum?
Not bouncy one.
The not bouncy one changes. Let's say that I'm going to cheat. Pretend the mass of these balls is 1 kilogram. That way I don't have to cheat, or that, right? So the change in momentum, you're going from 2 to 0. Delta P would equal what? I start at 2 and I go to 0. What's delta P?
-2.
-2. Sorry, I didn't hear you the first time. My bad. And that would be, again, kilogram meter per seconds. What's the change in momentum of the pink one?
-4.
Which one exerts more force?
Bouncy one.
Yes. Got it? And so this will show it. Yep. And so let me just run it. Notice it's right above that black doohickey. Almost knocks it over. Now this is the bouncy one. It's much bouncier. It's not perfectly bouncy, but it's a lot bouncier. Tried to put it in exactly the same spot. It exerts enough force to tip it over, whereas the other one didn't. So we see that this actually seems reasonable. Okay. Let me stop the share here for a second. And I know we've only got 3 minutes. I'm going to show you something for fun. Okay. Give me a sec. So if you really have to go, or if you're tired and don't want to pay attention right now, I understand. If you want to take off, I just thought I'd foreshadow something maybe for you here. Let me stop this. Let's do this. Okay. Oh. Hopefully it finds me here. Come on. All right. If you care, right, we could just create a new program. And you, like I said, if you want to learn this on Wednesday, that's fine. But I just thought I'd show you this. Let's say we say a ball is a sphere, right? And then let me do this. Let's just do this. Let's say the ball has a mass, which is, let's say 1, right? And let's say the ball dot position, let's say it just starts at the origin, 0 in the X, 0 in the Y, 0 in the Z, right? And then let's say the ball has a initial velocity vector. And let's say it starts from rest. Okay, and let's say there's a force exerted on the ball. That's a vector, right? Let's say it's 1 in the X, 0 in the Y, 0 in the Z. So we have a force in the X direction. And then let's set a time. Let's say we start the clock at 0, and I'm going to pick a small time increment, right? And so then what we could do is we could create a loop. So rate, I'm just going to do this as say, you know what? I'm going to do a quick thing here. I like to do this just because it ends up inevitably being useful. Like I said, if you want to get out of here, feel free to take off. Okay. And so the idea is this will display the simulation in real time. If I put in a 2 here, it'll be double speed. And if I put in a half, it'll be slow-mo, half speed. Okay, here's the idea, the Euler-Kromer relation. I don't know if you recall what we did, but we said first, update the force. Now, in this case, the force is going to be a constant right now, so I'm done. Then I'm going to update the momentum, and then I'm going to update the position. So if I want to do this right, let's do this. First, I need to figure out the change in momentum. And let me actually do it this way. The ball's momentum would equal the ball's mass times the ball's velocity, right? And so we could start making this code, and then inside of here, what we could do is we could say ball.p should equal the old value plus a little bit. It should equal the force times a small amount of time. So again, this plus equals just means add to the old value a small amount. Well, that's basically like saying this is the change in that. Okay. And then what we could do is we could say ball.v would equal ball.p divided by ball's mass. We're just code. All right. And so I'm going to stop here. But if you want, you could, well, we're almost done. But yeah, I know it's office hours and some people don't have a lot of time. So I'm going to stop here. This is foreshadowing how we could do all this in the code and animate stuff, right? Oh, I'm so close. Why not finish? Whoops, ball.v times dt, right? This is saying take the ball's velocity that you just figured out and multiply it by a small amount of time, and that's how much you change the position. And you say t plus equals dt. You add a small amount of time to the clock, you run it. Hopefully I didn't make any typos. There it goes. And you could animate the motion of this and you could see it in 3D and just swivel it around and you could zoom in and out. You'll be doing this in no time. Let's stop the live stream there. Woof.